Yeah. Hi everyone. Um, my name is Ria. I'm from the University of Sheffield. Um, so have you guys ever wondered why like moms are always the best at like finding any item in the house? Right? Do you guys uh, do you guys think it's because they know everything, or it's because they have better exploration, or because they are like, all right, I'm gonna say it's because they know how to exploit the knowledge that they already know about the home, right? So you go for it. I guess you have the best mom in the world. Yeah. Yeah. So this is very relevant to reinforcement learning because in reinforcement learning, it's a framework where we try to find optimal behavior, and this is done through the interaction with the environment, right? In this case, you're gonna have your agent that explores to gain information about the environment. Then from that exploration, then you can use it to exploit it to get the optimal policy. And then exploitation becomes effectively a very key thing in finding what is the optimal policy, right? And one of the open questions is essentially, uh, how do we determine whether an agent is doing an efficient exploration? And also, how can we effectively uh, basically quantify and evaluate these different exploration methods, right? And this is like one of like literally like a workshop that has been running since 2018. It's literally centered about around like solving these open questions. So we had a crack at it. And currently the solutions are, some form of performance or regret, or even like the number of updates to conversions, right? But however, I would say that while these do have meaningful, value um, and meaning in terms of how they describe, but they are also analogous to a scenario where you're trying to find, trying to lose weight or gain weight, but you're trying to measure what that weight is, but you don't necessarily have the ability to measure your weight directly. So what you do is you look at your running speed, and based on that, you're like, okay, I run faster today, so it means that I might have lost like maybe 2 kilos or something like that. Uh, but even though mass does contribute to how fast you run, there are a lot of factors that are involved in it, right? Like what you ate, how long you've slept, how long you've been practicing, all those kind of things. So you can't just lump it up to say because of your speed, definitely this is how much you have lost. And that's the reason why like it's essential that you find a way that you can like directly measure the efficiency or effectiveness of that. So what we did is we we're like, oh, we define what is an exploration process, right? Which is basically an interplay between exploration, exploitation, and also the learning strategy of your algorithm, right? And this is influences basically how your model updates from one policy to the next as it learns. And then with this, we're like, oh, we want to be able to compare literally different exploratory processes in a method that is task agnostic and as well is environment agnostic. And we wanted to capture exploration efficiency and be able to observe various characteristics of these exploration processes. And one of the things that we thought about was like, oh, we realized that we can tackle this basically by representing our policies as probability distributions over the state action space. And these are called occupancy measures, right? And the beauty about these occupancy measures is that for our stationary Markovian policies, they have a one-to-one relationship with the occupancy measures. And one thing that we know about reinforcement learning is that, like, as the learning process happening is taking place, there are sequence of evolving policies. So you started some initial random policy, and as time goes by, with every update, you will reach a final optimal policy or some final of epsilon uh, away from your optimal policy. But this as well has implications in terms as well, like the same sequence that you have, you're also going to have the same sequence as well with your occupancy measures because of the one-to-one relationship that has been established. And because now we have some probability measures or distributions, we can build an occupancy measure space, which is basically a probability distribution space. But then this allows us as well to use tools from information geometry. But those tools rely on this theorem that we as well proved that essentially, if ever your policies are smooth in terms of how they are parameterized, definitely you're going to have like a differentiable manifold. And this gives us the ability now to apply information geometry tools. So just an idea of what you're looking at, right? This space, or this manifold, it's not necessarily 2D. It's multidimensional. So this is just for the illustration purposes. But what you have is, assuming this is your initial policy, uh, your RL algorithm will move from, with an upgrade from pi naught to pi 1, just like that, and taking this C path all the way to pi star, right? But however, we know with imitation learning that if already like you have a data set of from your aspect, you can simply literally utilize supervised learning, and you literally kind of move from here all the way to there, right? Which is the shortest path on this manifold. And the other thing as well is this C is also the same C that you see in bold here. But down here, I wanted to indicate that like you have two parameters. One is moving from your policy to the optimal one, which we call distance to optimal. And the other one is moving from your policy to the next one, which we call like stepwise distance. And we sort of like put this in terms of X and in terms of Y. And you'll see later on because it's helped us in terms of giving us a visualization of what is happening. And one of the other thing as well is that in this space, we decided to use optimal transport distance, in this case, Wasserstein. But nevertheless, you can also use other information geometry matrix on the space. So what you have here is that first the visualization of our policies. Then we just literally just selected three policies. So on this vertical axis, you have updates, which show the time. So basically from time 0 all the way until like you reach convergence. So that's the reason. And here you have your y distance, which show stepwise. Then you have distance to optimality. And you can see over time, it goes to all the way 0, 0 because you've reached the optimal policy. And you will notice that in these, sure. Yeah, everything is discrete. Yeah, everything is discrete. Yeah. So thanks for that. Yeah. So for this illustration, this is a very simple 5x5 grid world where your actions are up and down, left, right. So it was interesting to just literally use that simple case to illustrate what this is. Yeah. And you want to say that as well, like in these two extremities, you find that the UCL2 basically is more stochastic in how it moves from one policy to the next policy, versus your soft actor critique, which is very reluctant basically to switch between policies. And then you find something in the middle, which is the posterior sampling RL. And then in this case, you see that like it tapers over time. So it starts with the high variation, and over time it gradually reduces until it reaches there. Right? And this basically gives us an idea, an insight of how these change or evolve. And one thing that as well you can determine is, when I was doing a poster presentation, I also illustrated this. You can pretty much tell which algorithm or algorithms are more stable as they reach the optimal policy, and which ones are more likely that whenever they reach the optimal policy, they'll go past this. And you can see this gives us that indication that if ever it reaches the optimal policy and you continue training, it's just going to go past it. And this is what is actually happening in reality as well. So we proposed two forms of exploration efficiencies, right? So the first one was like, oh, how about we compare this distance C with this L, and then we find that the ratio, and we call it the effort of sequential learning, which is basically C divided by L. And as I indicated, we're using Wasserstein, so that's what the W1s stand for. And also, then we also define what we call the optimal ratio movement. So in this case, you will see that if I'm moving from pi naught to pi 1, I'm essentially increasing my distance to optimal because my x1 is greater than my x naught. So in this case, we're going to say basically this step was a bit wasteful. It didn't necessarily help you to reach your optimal policy. But from pi naught to pi 2, we realized that our optimal distance to policy, basically distance to optimal, has been reduced. So this we consider as a useful step. So what we do is we collect a set of useful policy updates or useful steps, and we divide it basically by the total number of steps that we took, which was C. And it gives us a proportion of like how much useful steps were there versus how much was wasted. And in one experimental results, so this way we have our ESL and our OMR, and as well versus the number of updates. And you can see that our soft data critique is actually coming out right as a good explorer compared to the other ones. But one thing I wanted to indicate was look at the number of updates. PSRL has the best number of updates. So that kind of shows the dissociation that I was talking about in the beginning, that this number of updates, it tells you overall about the overall algorithm, but it doesn't necessarily exploit or explain much basically about like what's your exploration algorithm more efficient or not, right? This captures it more. But what's also more interesting is the fact that like, even though software critic is known as the state of the art, it only has about like 60% of useful steps. So that will tell you like how much work we need to do as RL researchers, that we need to find algorithms that are most useful in terms of the number of steps they take or policy transitions to get the optimal one. And this is for the 2D grid world as well, deterministic dense rewards. Furthermore, we came up with some theories as well to say, okay, this is basically our estimated distance bounds, error bounds for estimating this Wasserstein, because there's a lot of competitions that are involved in it, but we can use data sets to do that. And as well, this as well has a nice relationship with regrets in terms of like whenever you have an MDP that's Euler-Lipschitz rewards, then you're gonna have an upper bound bounded by our sum of distance to optimals. So now in a case where it's like you don't have an optimal policy, and this is where like sort of like regrets breaks down. We also find some nice correlation where we said, okay, actually, this eta sub is when you calculating your ESL without having your pi n is essentially not your optimal one, versus when it's optimal one, and then and this has this nice relationship. But as well, when we plugged in and did in practice, we realized that even though the magnitudes of numbers don't have much of a correlation, but in terms of ranking, they give us like a relative nice ranking comparison. So we can say, whenever you only have access to this, but you don't have that, you can essentially use it nicely to give you which one is a better explorer compared to the other one. And that kind of helps. And in this case, we use this on a more stochastic environment to illustrate there. So, yeah. So the key takeaways about this is that being able to see the polity trajectory in the occupancy measure space helps you to observe basically how your algorithm approaches the optimal policy. And as well, we saw that ESL and OMR can capture the efficiency of these exploration processes. And the number of days contain little information basically about how the policy evolves compared to the metrics that we proposed. And ESL and ESL sub can provide some form of, can provide the same efficiency ranking, and that helps in comparison in other. Yeah, so this brings the end of my presentation. Do you guys have any questions?